Hey everyone, welcome back to iTower. Today we're diving into a classic algorithm problem that you'll see all over coding interviews and algorithm courses, the Knapsack Problem. We're gonna break it down, understand what it really means, write a dynamic programming solution in JavaScript, and talk through every step so it actually makes sense. It sounds a bit intense, but trust me, by the end of this video, you'll feel confident with it. If you enjoy this kind of breakdown, don't forget to like the video and subscribe to iTower. It really helps the channel and makes sure you don't miss future videos like this one. Alright, let's get into it. So here's the setup. You've got a bag. Think of it like a backpack, and you can only carry a limited amount of weight. You've also got a list of items, and each item has two things, its weight and its value. The goal is to figure out which items to put in the bag so you get the most value possible without going over the weight limit. Let me give you a quick example. Let's say you can carry up to 5 units of weight. You've got 3 items. One weighs 1 and is worth 10, one weighs 2 and is worth 15, and one weighs 3 and is worth 40. You can't carry all of them. The total weight would be 6, but you can carry some of them, and you want to choose the ones that give you the highest total value. First, let's define a function called knapsack that will solve the problem. This function will take 3 arguments: an array of item weights, an array of item values, and the total weight capacity of the bag. Now, we need a place to store our results, so we can use a 2D array to keep track of the maximum value we can achieve for every combination of items and weight capacity. We'll create a table with n+1 rows, where n is the number of items. The extra row accounts for the base case when we don't have any items to choose from. For each row, we'll have columns representing weights from 0 up to the maximum capacity. Now we have our DP table, and it's filled with zeros initially. The idea here is that for each combination of items and weights, we'll calculate the best value we can achieve. We'll loop through all the items, starting from the first one. The outer loop will go through each item, and the inner loop will go through every possible weight, from 0 to the total capacity. In this part, we're checking for each item whether it can fit into the knapsack with the current weight. If the item's weight is less than or equal to the current capacity, then we have 2 options. We can either include the item or exclude it. We check if the item fits like this. Notice how I subtract 1 from I, because the array is 0 indexed and we want to access the correct weight and value for the current item. Now, if the item fits, we need to decide whether to include it or exclude it. If we include it, the new total value will be the value of the item plus the maximum value for the remaining capacity. If we exclude it, we just carry over the value from the previous row. Here, we're comparing 2 things. First, we take the value of the current item and add it to the best value we can get with the remaining capacity. Second, we look at the best value we could get without including this item. We take the maximum of these 2 options. If the item doesn't fit, meaning its weight is greater than the current capacity, we just carry over the value from the previous row. After we've filled out the entire DP table, the bottom right corner will hold the maximum value we can achieve with all the items and the full capacity. So, we just need to return that value. Let's test our function with an example. We'll use 3 items. The first item has a weight of 1 and a value of 10. The second item has a weight of 2 and a value of 15. And the third item has a weight of 3 and a value of 40. Our knapsack can carry a maximum weight of 5. Let's call the function with these values. When we run this, the result should be 55. That means the best combination of items is the second and third items. Together, they have a total value of 55, and they fit within the weight limit of 5. So that's the knapsack problem. It's all about finding the best combo of things you can fit within a limit. Dynamic programming helps us avoid redoing the same calculations over and over again, and this pattern comes up all the time, not just in knapsack problems, but in tons of real-world optimizations too. If you found this helpful, I'd love it if you gave the video a like and subscribe to iTower. And if you want more algorithms explained just like this, let me know in the comments. Maybe we'll do coin change or longest common subsequence next. Thanks for watching, and see you in the next one.